Hello guys, in this video we're going to look at evaluating definite integrals using infinitesimals. We're not going to be using limits at all, just algebra and infinitesimals. What is a definite integral? Let f of x be some defined function. That's just a graph of a random function. It can be any function. The definite integral of f of x would be the area under the curve between two defined x values, a and b, where b is greater than a. The common notation for an integral is you got a at the bottom, the little squiggle, then b at the top, and then your function, f of x, then dx. So that is the definite integral from a to b with respect to x of the function f of x. So what this means is that if you evaluate this integral, you'll get the area under the curve between a and b on this function. You'll essentially be getting the area of that green shaded area. So how can we find the area of that under a curve between 2 points? We can attempt to find the area using trapezoids with differing heights. The area of this polygon is the average of the two heights multiplied by the base. So as you can see, it's like a rectangle almost, except the heights are different. So it's a trapezoid, and to get the area of this, you just need to get the base, multiply it by the average of the two heights. So you add height 1 plus height 2 times the base, or divided by 2, then times the base, and you get the area of this shape, this polygon. We're going to be seeing this polygon a lot. So approximating the area, using one of these polygons, we can approximate the area under the curve. So what I've done is I've created the polygon, except on this, I've evaluated the function of x and put the top of the polygon here, and I've evaluated the function a and put the top of the polygon here, and evaluated the function at b and put the other top there. And this is an estimate of the area under the curve. Using two of these polygons, you can get an even better approximation. So as you can see now, I have 2, and it's even closer to the exact area. And now I have 4, and look how close it is to the actual area. The more polygons we use, the more accurate of an approximation our area is. So n here is the number of these polygons we have. As n and the larger n gets, the better our approximation is. So let's generalize this idea as a formula. So the area of the curve will be roughly equal to the sum of all the areas of the polygons. So if we sum up all the areas of these polygons, we get the area under the curve, or just an estimate of it at least. So therefore we can simply insert the area formula into the summation where n is the number of polygons used. So on the bottom here I have a summation. So it's going to sum from I equals 1 to n, and it's going to sum up all the polygons, so all their areas. So the areas will be height 1 plus height 2 divided by 2 times the base. So, but to actually use this, we first got to figure out what is height 1, what is height 2, and what is the base in order to complete our formula. So height 1, or h1, is the function evaluated at the right-hand side of a given polygon. For example, x1 in the image is the right-hand side of the first polygon. So x1 is height 1, x2 is height 2, x1 is height 1 of the first polygon, x2 would be height 1 of the second polygon, x3 would be height 1 of the third polygon. So it's height 1 is always on the right-hand side of the polygon. It is equal to the width of the first polygon plus a. So if we take so x1, you take a and you add the width of the first polygon and you get to x1. x2, for another example, you would take a and add it to the width of the first 2 polygons. So if we wanted x3, we would just get a and add it to the width of the first 3 polygons. Since the width of all polygons are equal, since we're dividing this into equal parts, that means the value of any xi can be expressed with this equation. Xi equals a plus b minus a divided by n times I. So we're taking the distance between b and a, and dividing it by how many polygons we have, and multiplying it by I, then adding it to a. So if I say, like, what is an x of 3, I would evaluate this value first, then I would multiply it by 3 and add it to a, then I will get x of 3. The height of the polygon on the right side, so x of 3 just tells you this vertical line right here. But if we actually want the height where it hits the function, h1, then you simply evaluate the function at that. So if I want this actual y value right here, I evaluate the function at x1. So I've just taken my a plus b minus a over n times I, and I've just evaluated it at the function at that point. So I have f of a plus b minus a over n times I. So now we have height 1, but we still need to get height 2. And as you can see, the base is b minus a over n because the base of the polygons is always the same. It's always b minus a over n. So the left-hand side of a given polygon would be equal to the right-hand side minus the width of the polygon, essentially being xi minus 1. So it's the same thing, a plus b minus a over n times I, but the only thing you add is you subtract the width of one polygon. So why do you do that? Because if I'm at the left-hand side of a polygon, and I want what's at the, or if I'm at the right-hand side of a polygon, and I would want what's on the left-hand side, I just have to subtract the width of this polygon and I get to the left-hand side. So now all we have to do is we have to replace h2. We have to evaluate the function at at xi minus 1, and that's how we get height 2. So now we have a new formula where we've replaced height 1, height 2, and the base. Multiplicatives by a constant within a summation can be removed from the summation. So this is just a rule of summations. If you're you could just play around with this yourself and test it with numbers. If you're just adding a bunch of numbers together and you're multiplying by a constant every time, that's the same thing as just multiplying that constant one time after the summation. So here I'm essentially multiplying this up here by 1/2 and then multiplying it by b minus a over n. So I pull both of those constants out, and so I put b minus a over 2n on the outside of the summation. And now the inside of the summation just has the two functions that you had to evaluate. So as the value of n gets larger and larger, the results of the formula get closer and closer to the true area under the curve between a and b. So as you can see, when n is 1, we get the area of just this one polygon. When it's 2, we get the area of the sum of these two. When it's 4, we get the area of the sum of these 4. So it gets more and more accurate the larger n is. And so technically, if n was, if it like reached infinity, we would get the exact area. But the issue is, if infinity is not an actual number we can work with, so we can't just plug infinity into this equation and use it. So it still needs some work. You can implement this in JavaScript. The function becomes more accurate the larger n is, so this would be the code for it. You start with sum equals 0, you go from I equals 1 to n, you sum up the two functions, and at the end you multiply the sum by b minus a over 2 times n, and return the sum. And so if you pass a function in there, the a, the b, and then a large n value, let's say 100, or maybe like 10,000, the larger it is, the slower it runs. You will actually get an estimate of your integral. So this is just a definition of which you probably should plug into the function for n. You want a number greater than or equal to 1, but less than infinity. You actually have infinity in JavaScript. If you try to plug infinity into there, it probably won't work. And n is a subset of all the integers. So you usually want to plug a whole number in there. Fractions might work, but I would go with just whole numbers. just integers. Deriving the definite integral formula. So I told you the formula as it is, it won't really work. We can only use it, as I showed with JavaScript, to get estimates and not exact answers. So we're going to derive a new formula. So in order to get the true value under the curve, the width of each of the polygons must be infinitely small but not 0. We can call this value epsilon, being defined as the value infinitely small but greater than 0. Imagine a decimal with an infinite amount of zeros with a 1 somewhere at the end. So you have epsilon equals 0.000000, and these zeros go on forever. They never stop, but somehow right at the end there's a 1. So it's essentially this number is not 0, it's bigger than 0, but any number you can define besides, any positive number you can define besides 0, it's smaller than. So it's infinitely small but not 0. This is called the infinitesimal, but I'm just going to be calling it epsilon. The width of each polygon must be equal to this infinitely small value, because as you know, I said as you increase n, the width of the polygons gets smaller. So when n is equal to infinity, that means the width of each polygon is going to be infinitely small, but not 0, because the equation doesn't work if it's 0. So what I've said is I said epsilon equals b minus a over n, because b minus a over n is the width of a single polygon. Rearranging this equation, we can find that the number of polygons needed to accomplish the distance between b and a divided by the infinitesimal. So what I've done is I've multiplied n on this side, and then I've divided both sides by epsilon. So I get n equals b minus a over epsilon. So now anytime I see n, which originally had to be infinity, which I can't use, I can just substitute n with b minus a over epsilon. So here I have our formula we originally derived, and what I've done is anywhere there's an n, I've substituted it with b minus a over epsilon. So here we had b minus a over n, that becomes b minus a over epsilon. Then I just simplify it. So as you can see, I took this formula and I've just simplified it. So on the outside, b minus a, 2 times b minus a over epsilon, that simplifies just to epsilon over 2. Then you got like right here, b minus a over epsilon, that just simplifies just to epsilon. So all these inside simplify just to epsilon. So this equation actually looks a lot simpler. So this formula we have derived is equal to the definite integral when integrating from the smaller value a to the larger value b, assuming b is greater than or equal to a. So if we're integrating from a to b of a function, we can use this formula we just derived. If integrating from the larger value b to the smaller value a, assuming b is greater than or equal to a, the negation of the formula is used and a and b are swapped. So essentially, if you're integrating instead of from a to b, you're going from b to a, so you've got the larger value on the bottom. What you do is you take the same formula, but you swap all the a's and the b's. So a's become b's, b's become a, and you negate the whole thing. So you essentially get the same answer. If you just flip a and b around here and do the normal formula, you will get a positive answer. And if you just add a negative sign to that, you get the you get what happens if you do the larger value on the bottom. This can be implemented in JavaScript as a function. The function becomes more accurate the smaller p is, but p can't be 0. So this is the function. It's the same thing we just mentioned here. So f, a, b, where p is essentially our epsilon. So that's your infinitesimal, but you can't actually use an infinitesimal in JavaScript. But what you can do is just make p really small. So p can be anywhere between 0 and 1, but it can't be 0. But it can be 1, and it's a subset of all the real numbers. So you can say like 0.0001, and the smaller it is, the more accurate this will just give you an estimation of the more accurate of an estimation of your integral will give you. So we're going to do an example where we're actually going to derive the real, we're not going to estimate a value, we're going to actually derive the real value from an integral. So, as the math can get quite complicated, let us simply define the function as f of x equals x. So this is just a very, very simple function. The reason I'm using such a simple function is just because it will be very easy to do, because this can get very complicated. We will integrate between 3 and 5. So we will be integrating that area under the curve. So as you can see, I got 3. The function is just x, and we're integrating from 3 to 5. Given the simplicity of this function, we can calculate the area of the curve without using integrals first in order to confirm our answer later. So recall the area of this type of polygon is the average of the two heights times the base. So here, setting the value of the integral between 3 and 5 equal to the area of the polygon, we calculate the integral simply to discover it is equal to 8. So I've just, the integral in this case, the integral just in this case is equal to this. Your integrals, usually your integral is not equal to this. It just happens in this case that this integral is equal to this. So we substitute in, to get the heights at the positions, 3 and 5, you plug in the x values, and then we divide by 2, but since the function is just x, we just get 3 and 5 back, divide by 2, we get the base, which is b minus a, 5 minus 3, 8 over 2 times 2, it gets 8. So we know the area under this curve is 8. So when we actually go and apply the formula we learned earlier, we should get 8. If you get 8, that means you did it right. We can now set up the problem which to solve. So this is the formula we derived earlier. So if we're going to integrate from 3 to 5, with respect to x for the function x, we're going to take this formula and we're going to substitute everything in. So as you can see, I substituted in the b, 5 minus 3. For the a's, I substituted in 3. And now we can actually solve it using this formula. So the first thing I do is, here's the formula again. And what I do is if we look down here, you can see that I have essentially removed the parentheses, and I have solved up here. So 5 minus 3 is 2, so we just got 2 over epsilon over here, and then I've just removed the parentheses because it's just addition, so you don't need them. And then down here I have actually done the addition, so 3 plus 3 is 6. Epsilon I is going to be 2 epsilon I, then minus epsilon. So here, what I've done is I've just put parentheses around 6 minus epsilon. I just put parentheses around them to make it clear what I'm going to do in the next step. What I've done here is I've pulled 6 minus epsilon outside of the summation. So you're saying, why would you pull it outside of the summation? Because I have by here, because when I have the word by, after by, that's just me explaining the rule which says why you can do this. So if you have any summation where I equals 1 to n, and you have some function plus a constant, which I called z, you can pull that constant out of the summation if you multiply it by n. The reason is because if you're going, because n is how many times you're doing an addition. So if let's say a constant is 3, and n is 3, that means you're going to be adding 3 to your f of x, I, 3 times. So if you're adding 3 to it 3 times, that's 9. So you can take the 3 out, and then you can multiply it by how many times you're adding it, and that would be your n. And so that will give you the same thing. So here I pulled 6 minus epsilon out, and I'm multiplying it by 2 over epsilon. And then here I just simplify it. So I just actually do the multiplication, and I get 12 minus 2 epsilon over epsilon. Now here, I pulled another thing out. I've pulled 2 epsilon out. And the reason I've done that is because if you have any function, or if you have the summation, and every time you multiply by a value, so if I have a constant, so here I have z times f of xi, if I'm multiplying by this constant every time, that's equal to just the constant on the outside. So I can pull the constant out. So I've pulled 2 epsilon outside of my summation. Now this is another rule. So if you have summation I on its own, so I equals 1 to n in just I, that's going to be equal to n squared plus n over 2. So here I've just taken my n, which is 2 over epsilon, squared it, plus added it to 2 over epsilon and over 2, and I've just replaced the summation of I with this. Now what I've done, I've actually carried out this, I've actually done the squaring of it here. Then here I've multiplied 2 epsilon into this fraction, and then I've simplified it again, and then here I've multiplied this fraction by epsilon and this one by 2 in order to make the denominators the same. And then here I just, since now the denominators are the same, I just link the 2 fractions together. As you can see, 4 epsilon and negative 4 epsilon cancel each other out. Then I just have 8 plus 24, and that gets to 32. Now I multiply 32 by epsilon and 2 epsilon by 2, and I get 32 epsilon over 4 epsilon, and the epsilons cancel out, and we just get the value of 8 as our answer. We can also use one of these 2 functions we created earlier to evaluate this integral. So I would define my function of x as just return x, because that's all the function is just x. Then I would say alert integral n f, 3, 5, 1000. Or here I could say integral alert f, 3, 5, 0.001. So this is integral n, the one where we